Okay, thanks for coming to class, the few and brave of you. So we have an exam a week from today. It's going to be pretty different than the other exams because it's going to be like multiple choice, maybe short answer. So we haven't really had any homework or assigned or chance to practice derivations. So just testing you on kind of topical knowledge from the notes. Any questions? Yes.
Are you going to upload any sample?
I don't really have, I don't have any examples. So it's just kind of like, multiple choice questions on concepts from these last few chapters.
Okay, it's starting unit 8, right?
So starting where the previous exam didn't cover.
We have this and then a final, right? This is not the final.
There is no final exam.
Okay,
There's just this exam and then the final project.
got you.
Yeah, which is due just before the final exam period starts.
Gotcha.
Okay, all right. Any other questions? Okay, good. So, we've been talking about clustering, and we learned about the k-means algorithm, and then we learned about document clustering with the bag of words model, and in particular these TF-IDF scores, and we tried k-means for this clustering these Usenet news groups, and we found that two of the clusters very much corresponded to the ground truth categories. One of them seemed to be split between the alt atheism and the talk religion MISC, and then the other one was kind of distributed across all the categories. So it didn't seem like it was completely successful. So there's another approach that we can apply to clustering, which is low-rank matrix factorization, which we learned about in the last unit. And we have learned about two methods to do that, basically the SVD, which was used for PCA, and non-negative matrix factorization. And so the way we can think about this, how does this do clustering for us? Well, if we start with the data matrix where we have n documents going down the rows and d terms going across the columns, and we do a low-rank matrix factorization, say like this NMF one, then we get these vectors here. There's going to be, and let's say we choose a rank capital R. So we get these vectors here. There's going to be R of them. And then we get these vectors here, and there's going to be R of them. And so in some sense, you could say, if you look at any document in the data set, so that would correspond to a row here, you could approximate that by the same row here times this entire matrix, right? Just from the linear algebra. And so if you think deeper, well, so that decomposition says that this document can be written as a number of scalar values times these different term vectors. So it sort of suggests that each one of these rows here is like one kind of set of, or each row is like one topic. So, and by topic, I mean, if you looked at the different terms in this row, you would notice a certain pattern to them, or flavor to them. If you look at the terms over here, you'd notice a different one, and so on. So somehow just doing this low-rank matrix factorization, you sort of implicitly say that any document can be written as a weighted sum of these R term vectors. And that tells us then that these are the building blocks of any document. And so it's sort of like saying in this model, there's like capital R different kind of fundamental or canonical documents. And any document in our database is just a weighted sum of those R kind of fundamental documents. So, and those documents, each one has a collection of words for a particular topic in this case. And we're just letting the matrix factorization do all this organization for us. We run it to minimize RSS under this non-negativity constraint, and it comes up with this sort of explanation. You can also think about it the other way. You can say any word here has a distribution across documents, and so this sort of suggests that there's R kind of fundamental types of document, and any word can be thought of as a linear combination of those, R documents. So you can think about it in either way. Any questions? That's kind of the main idea here. What we're saying that's why matrix factorization kind of implicitly gives us a type of clustering. In particular, this is called a topic model. Is that idea sort of making sense? Okay. And then with the SVD, we do have this sort of diagonal matrix. So there's, you could either say that this is a tall matrix and this is a wide matrix, or you could say that this is a tall matrix, this is a wide matrix. As we know, all this does is it scales either the rows or the columns. And the main property with PCA or SVD is that these guys are all orthonormal, and these are all orthonormal. And so even if you multiply, even if you consider that as one thing, these will be orthogonal. They won't be normalized anymore, but they'll be orthogonal, and then these are still orthogonal. So SVD does the same sort of thing where it tries to give you this R topic model, but it is in some sense constrained maybe to give you orthogonal topics, whereas NMF is constrained to give you non-negative topics. So that's sort of the difference. And you could then ask the question like, is orthogonality important if I'm breaking a document into these building blocks? Do I want the building blocks to be orthogonal or not? What's especially kind of strange about applying the SVD to our current TF-IDF features is that those features are all non-negative. And once you apply an SVD to them, you end up getting like these new, these will have negative values. So they're no longer like TF-IDF features. They're some other like building blocks to get them, but you sort of took a departure from the spirit of the original model. Whereas with NMF, because it keeps everything positive, you can really think of these still, if you want, as TF-IDF vectors, and maybe some like linear combination of them to make any document. So that's the difference, is the constraints that they impart on the factorization. Okay, and just terminology, people, when you apply SVD, or sometimes people say PCA, to this problem, it's called latent semantic analysis. Okay, so let's see how this works. So we'll start with the SVD approach. We apply it in the demo, and we look at the results. And maybe let's look at the confusion matrix first. We can see that there's two of these principal components are pretty well focused, but not nearly as good as k-means. K-means was like, close to 100%, and these are like 70. And then we can see this one is sort of, kind of evenly split. But then this one is kind of uniform, sort of like it was for k-means. So not really very successful. I would say less successful than k-means. Yeah, for example, if you look at this principal component and you look at the terms in it, you have like a mixture of space terms and religious terms. So you can just see that something seems wrong about that. Okay, so that didn't work well. What about NMF? So NMF, a pretty good clustering of these. Maybe not quite as focused as we got with k-means. And then we have these two others are sort of pretty well split between alt-atheism and talk religion myth. And so you could say, well, maybe it wasn't the best clustering, but then remember that there's a natural overlap between what happens in these news groups. And when you actually look at the words that are most important for the 0 and 3 components of NMF, you actually see that there is quite a good pattern here. So these are all very much religious words, whereas I would say that these are more like ethics, morality. And so I think what this model has done is it actually has done a very nice clustering of the data where you have religion and morality separated. And it just so happens that the news groups, they actually combine those things in each news group. So I think this actually was able to really find the structure in the data even better than the ground truth labels were doing. Okay, so NMF was pretty successful here. And you might also then wonder, like, well, what about these? Even though it doesn't match the ground truth labels as well as k-means, maybe it found a better way of explaining the data that actually had some overlap between those two kind of ground truth categories. Maybe it like figured out a better categorization than those two things. Okay, so that's just showing you now we've seen 3 different types of clustering, k-means, and LSA and NMF, so various options. Any questions on this last approach? Yes?
Yeah, sorry, I'm a little bit confused here. So these words, we set these words, or these are the output of the algorithm itself?
So let's say for NMF, we have, this is the data. So each one of these rows are the TF-IDF features for each document. And we run NMF, and it gives us this decomposition. And now if you look at these vectors, notice that these are d-dimensional, which is how many terms we have. These you can think of as TF-IDF vectors. So like so I mean, okay, so like the first column here corresponds to like the first word in our vocabulary, right? Second column, second word, and so on. So that's, that is preserved here. The first column of this corresponds to the first word. Next one corresponds to the second word, and so on. Okay, so we can think of those as importances, a vector of numerical importances for every word in our vocabulary. But in another sense, they are kind of like fundamental building blocks of collections of words that can be linearly combined with those coefficients to build any document. Okay? And because they're all non-negative, we can continue to think about them as TF-IDF features, something where 0 means it's not important, and the larger it is, the more important it is to categorize that topic now. So the list of words I showed you what we do is we look at all the numerical values here, and we just sort. So like the largest numerical value, maybe that corresponds to this term. The second largest was maybe over here, third largest here, and so on. And then in printing this list, like this was the term with the largest TF-IDF feature in that topic, right? And this is the second, third, fourth. So this is sort of in importance. These are the words that are the 10 most important words for that topic. And of course, this continues going. There's like 38,000 of them. But I'm just showing the first 10, because those are the ones that are most important. Right. Yeah. Sure. Okay, great. Any other questions? Okay, so yeah, I think NMF is a really cool idea. And then we're going to talk about one more approach to clustering, which is very similar in spirit to k-means, but it has more of a probabilistic flavor to it. K-means is kind of heuristic, and it's sort of a nice, simple idea. And this approach is a little bit more robust, flexible, and has a probabilistic flavor. And it is based on these things called Gaussian mixture models. So let's first talk about, let's review Gaussians and then talk about Gaussian mixtures. So Gaussians, in one dimension, we have like a bell curve. It has a mean and a standard deviation that tells us how wide it is. And in 2 dimensions, the PDF would look, something like this, where you have some kind of spread in both dimensions. This is the height of the PDF. And so the mean would be the 2-dimensional vector that is at the center of this. And there's a covariance matrix that tells us how things are spread, So what's interesting is that when you look at that covariance matrix, Q, if you take the eigendecomposition and you look at these eigen vectors, they are the ones that tell you exactly how these are pointed. So, okay, if you take a slice of this PDF, you take a slice like at this probability level, you get a shape here that is an ellipse. And then you take a slice deeper, this is a bigger ellipse, and so on. So all the slices are ellipses. This would be just if you generated samples from this PDF, you again see this kind of, this sort of elliptical behavior here. And now if you look at the principal axes of that ellipse, they're exactly given by these eigenvectors. So in this is a 2x2 Q in this illustration. So each one of these V's is a 2-dimensional vector, and they tell you exactly how that ellipse is oriented. And they're going to be orthogonal, as we know. So in 2 dimensions, once you know the first one, the second one is, you know what that's going to be. And that's also true of ellipses, right? The principal axes of ellipses are always orthogonal. So then, the other thing about ellipses is that they're stretched. It's stretched possibly different ways in those 2 axes. And it turns out that the eigenvalues, in particular the square root of the eigenvalues, tells exactly how much it's stretched. So that's kind of a cool thing about eigendecompositions of covariance matrices, is they break down the shape into how it's pointed and how much it's stretched. Okay, so the shape of the PDF. So principal axes and stretched. Okay, so this is the expression for this Gaussian. So this is a probability distribution over a random variable x, and it has a mean and a covariance matrix, and this is the form of the PDF. And here we have this exponentiated quadratic form, and then we have a scale factor that ensures that when you integrate this over x, it integrates to 1. So that's really what this is doing. Okay, so this is just a review of the multivariate Gaussian distribution. Any questions? Okay, so now a Gaussian mixture model is where you have a sum of those PMFs, and they are scaled. Each component in the sum is scaled by a scalar that I'll call gamma k, and these gamma k's are all non-negative, and they sum to 1. And essentially, if you visualize a Gaussian mixture, it's like a collection of Gaussians. Each one has its own mean and its own covariance. So you can see the mean and the covariance of these two Gaussian components are different. And then these gamma k's tell you the probability that points are drawn from one or the other. So if gamma k is, it's like 0.9 and 0.1, you would see, about 90% of your samples are coming from here, and only 10% are coming from here. So that's essentially what the Gaussian mixture does. So you can immediately see that these gamma k's are actually like the values of the probability mass function that tells you which of these mixture components samples are drawn from. Okay, and so if we have data and we can then fit this Gaussian mixture model, we'll talk about how to do that. It's a little bit complicated, but let's say you can fit the Gaussian mixture model to the data, like what happened in this picture. They were given these samples, and they were able to, to fit the parameters. So you have a mean vector covariance matrix, mean vector covariance matrix, and then these two scalars. So they're able to fit that. And now, given any point, let's say this point, if we want to cluster this point, it essentially comes down to saying, if there's a point here, what is the probability that that point was generated from this mixture component versus this mixture component? And if the probability of this point was larger from here, then you could say, yeah, it's more probable that that point came from here, so I will cluster that point with the blue cluster. And what you end up getting is you end up getting a decision boundary that is that's not linear. It has kind of a, I don't know, smooth shape that goes through these. So it's it's definitely different than k-means. So k-means, you would have like these two centroids, and then you just, in this case of k-means with two components, your decision boundary would simply be the line that bisects your centroids, right? Whereas in GMM, it's because you have like these different covariance matrix and curvatures, the probability of where things are 0.5 is some more sophisticated shape. So it's similar in spirit to the Gaussian mixture, to the k-means clustering, but it's probabilistic and a little bit more nuanced. So that's the idea. Any questions on the idea? Is that making sense? Okay, so that's here. We cluster a test point, test X, by determining which GMM component K is most probable. So here I'm just indexing the components by K. So it's like the kth mean, kth covariance, and kth weight. Okay, so to see this a little bit more in the math, we want to think about hierarchical probabilistic models. So hierarchical models you can think of as like multi-stage models. And in this approach, we just need a two-stage hierarchy, which kind of goes like this. If you think, okay, let's say someone told me I have this Gaussian mixture model, and then they asked me to generate samples from that model. How would I do that? Well, you would do it in two stages. First, you would think like I have a binary random variable, like does my new sample come from here or here? And depending on these, you would first draw that binary random variable, and then you say, okay, now that I know that it came from this sample, well, that's just Gaussian. So conditioned on the fact that it came from this, it's Gaussian, and there's standard ways to generate points from a Gaussian distribution. So that's kind of the idea here. We have a two-stage approach to generating this random vector. First, we're going to draw a component index. We'll call the index kappa, and kappa is going to be an integer here between 1 and capital K. Capital K is the number of clusters in our model. And we're going to draw it according to this PMF, right? The gammas, as I mentioned before, these are the values in a PMF. They're all non-negative, and they sum to 1. So it's a valid PMF. So another way to write that is the probability that kappa, the random variable, equals any number k is just lambda sub k. Okay, so that's the first stage. We've drawn this k-ary discrete category, if you will. And then second stage, now that we know k, is pretty straightforward. We draw x according to this Gaussian PDF, where notice that we plugged in, actually, we drew kappa, and now we're going to use kappa to evaluate, we're going to evaluate the kappath Gaussian. We're going to draw a point from the kappath Gaussian. And so here, we're sort of implicitly using this model. Probability of x, given that kappa is k, is this Gaussian, where we have k here. Okay, so those are the two kind of stages in our hierarchy. And maybe to see this just from math alone, without even any intuition, we know that if you have a joint distribution, so this is the probability density jointly of x and kappa being k, and you integrate or sum out all the possibilities of this random variable, then we know from probability theory then that kind of takes that out of the equation and you just get this. Okay, so hopefully you kind of agree with this equality. And now we have another fact from random variables. The probability of A and B is probability of A given B times probability of B. So we can apply that to write this like this. Probability x given kappa times probability kappa. Here, it's a little bit more complicated because x is a continuous random variable and kappa is a discrete one. So in some cases, we write this as a probability density with a little p. In other cases, we write it with a capital PR, saying this is the probability of this event happening, the event that kappa equals k. And finally, we take our, we know that, probability of x given that it came from the kth mixture component is just this Gaussian, and the probability kappa came from k is just this value. So this is just sort of a way that we can use these ideas and reconstruct the expression we started with for our Gaussian mixture. Okay, so what's interesting is that the original PDF that we're dealing with is just over x. There's no other random variables. This kappa is something that we kind of invented for our convenience. And so this is called a hidden variable. And there's millions of ways to come up with hidden variables to rewrite probabilities in terms of multiple variables. So here we're starting the probability density over x, but then we're rewriting it as some combinations of probabilities over x and kappa. And it just so happened for what we're doing now, for clustering, this hidden variable kappa is exactly the one that we want to use. There's many other ways to rewrite this using other hidden variables that maybe are useful for other applications. So it's almost kind of like an art of rewriting a PDF using hidden variables in a way that are going to be useful for whatever you're trying to do. Okay, so that's the idea behind hidden variables and hierarchical probability distributions. All right, any questions on that? Okay, so, all right, so let's assume that the Gaussian mixture model has been trained, so we know it, meaning we know these parameters. We know our covariances, our means, and our gamma k's. And this is the expression we just derived on the previous page. And so now the idea that we want to use for clustering is we're given X, we're given the sample, the test sample, and we want to compute the probability that X was generated from component K. So this is like a hypothesis. So we want to do this for all the different K we have. What's the probability it was generated from the first, the second, and then we can look at them all and see which is largest. So that means that this is really the thing we need to derive. The probability that kappa equals K given the value of the sample X. So as you can notice, this ordering, kappa given X, is opposite this one, X given kappa. So we need to kind of swap these. And if you remember, Bayes' rule is the kind of probabilistic tool that allows us to swap conditioning. And Bayes' rule tells us, okay, you can swap it, so you get X given kappa, but then you have to write probability kappa there and probability X here. And Bayes' rule comes from this kind of simple idea, probability A given B times probability of B. Maybe I'll just, sorry. We just saw on the previous page that this is the same thing as a joint probability, but we can also write it the other way, probability B given A times probability A. Right, these are both, I think, things that you agree. And then if we can do that, then that means that we can move this to the denominator of the other side, and we get probability A given B equals probability B given A, probability A divided by probability B. So that's where this equation here comes from. Okay, and the nice thing is we know exactly what this is. That's this. We know what this is. That's this. And this thing is the entire thing. We know that too. So it's really just this. So we plug that in down here. We have to be careful not to reuse this this value K, because K is fixed here. So we use K prime in the denominator. Okay, so with a trained model, we know all these parameters. We know our test point X. We can plug them into this expression, and we can compute a probability value, a number between 0 and 1. We can do that for every hypothesized K. And so these are called soft assignments. So you might, like coming back here, you might say for this point, it's with probability 0.6, it's coming from here. Probability 0.4 is coming from here. This point over here, okay, probability like 0.95 coming from here, probability 0.05 coming from here. So those are the values we're computing here. Now, you might say, I don't really need that level of detail. I just want a hard assignment. I want to know which is the closest cluster. So if you have this vector of PMFs, all you need to do is look for the largest entry in that vector. We do this with the argmax, or the index of the largest entry, and that tells you this is the cluster that is most probable that it's come from. So that would be the hard assignment. Kind of like a hard decision versus soft decision in classification. Okay. Okay, so that's the idea behind clustering with this GMM that's been trained. Any questions on this part? Okay, so let's just do a summary, everything together. So we start with our full data set of all of our samples X, going from I equals 1 to n. We didn't cover the details, but the first step is to fit the GMM parameters to this data. So let's say we can do that. And then we have 2 for loops, nested. So for each sample I in our data set and each hypothesis K, we compute this soft assignment from the previous page. So this is the probability that the ith sample came from the hypothesized cluster K, given that xi is the value of that sample. So we can compute, for all I and all k, these numbers, and then for each one of the samples in our data set, we can compute the hard assignment. So when we're done with that, for all the samples in this data set, we basically have two categories, blue or red. And so like the things have been colored according to the final label that the GMM classification gave us. Blue or red. Okay, so this is what we have covered so far. This is how we do GMM-based clustering. The thing we haven't gotten into are how to do this fitting. Any questions on the clustering part before we move on? Okay, so let's now talk about the fitting. So we would like to use maximum likelihood. That's how we've done things all semester. So we want to find the parameters theta. So theta is all these learnable parameters that maximize the likelihood. So they maximize the probability of our data given those parameters. And we also know that we can sneak this log in there because often the log makes our life easier. In particular, if all these samples are IID, then we have a big product over I, and when we take the log, that turns into a sum over I, which is way more convenient. Okay, so let's say we do that. We plug in our expression. We get the sum of the log, and then here is our Gaussian mixture model. And this is our log likelihood. Now, unfortunately, it's not as simple as when we had a single Gaussian. If we had a single Gaussian, then because this is like e to some quadratic, the log takes out the e, and we get this nice quadratic model, right? And we can actually solve that in closed form. But we have a log of a sum of exponentials, and there's no way to simplify that. So this is kind of as simple as we can write the log likelihood. And it's actually quite a challenging thing to deal with. It is non-convex. It's difficult to maximize. For example, if you did something like gradient descent, that's just not known to work very well for this. You should probably get stuck in a local minimum. So instead of, there's a very popular algorithm called the EM algorithm. How many of you guys have heard of the EM algorithm? Curious? Expectation maximization. So that's what we're going to talk about. We're going to talk about the EM algorithm. And the EM algorithm is actually, it's not just used for Gaussian mixture models. It's used many times where you have this crazy likelihood that, that you just don't know how to maximize. And it's non-convex, and you're just looking for some way to get, maybe not the global optimum, because there's really no way to do that if it's non-convex. There's almost always no provable way to do that, but you just want to find like a pretty good solution. And that's what we have here. Okay, so we'll talk about expectation maximization. Now some of this looks a little bit complicated, but we'll go through it and provide a lot of intuition. So at a high level, EM is an iterative approximation algorithm for generic maximum likelihood estimation. It is guaranteed to converge to a local maximum of the likelihood. Now, you could say, well, gradient descent would also be guaranteed to converge to with a small enough step size. But I think this generally works better than gradient descent. But the key just to any method is if you have a good initialization, then this can give you a much higher chance of success that you avoid a bad local minimum. Okay, so the thing about the EM algorithm that's different from gradient descent is it uses this idea of hidden variables. So the original log likelihood, as you can see, there are no hidden variables in here. We just have like weights, Gaussian terms, log, sums, right? We don't have that kappa in there. So when you apply EM, you actually need to figure out, or you need to declare what your hidden variable is. And as I said before, there's many, many different ways to use hidden variables. Some will work well, some won't work well at all. So there's sort of an art to applying EM to a problem. Maybe you'll try various types of hidden variables. And in some cases, you'll find that you just can't derive it, it's too complicated. Or in some cases, it's simple, but something fails about it. For our Gaussian mixture model clustering, we kind of know what we want to do. We want to bring in this kappa as our hidden variable, and then we have, you know, a model over kappa as one probabilistic variable, and then x is the other one. Okay, so for this derivation, we'll try to be a little bit generic, and instead of calling the hidden variable kappa, we will just have a matrix Z of hidden variables. So this is just sort of generic EM applied to any problem. And we want to maximize our parameters, maximize over our parameters, Z, and then X is our data. So the EM algorithm basically alternates between these steps, just repeats these two things over iterations T. T is like 0, 1, 2, ... And when you look at this, it just looks really complicated. So what do we have? We have, this is our log of our joint probability of our data and our hidden variable. And we assume that this probabilistic model is somehow dependent on the parameters we're trying to tune. And then we have an expectation. This expectation is over the random variable Z, conditioned on our data X, because X is a fixed known for us, it's our data. And this is also conditioned on our previous guess of what the thetas should be. So this function that you get when you take the expectation is going to be a function of theta and your previous guess. Your previous guess is fixed. This theta is treated as a variable. So in this E step, the expectation step, you compute this quantity, and it gives you this Q function. And then in the M step, you maximize over the Q function. So this is fixed, and you find the theta that maximizes this, and you say, that's my next guess, my guess for the next iteration. So now then this, next iteration, this becomes your guess. You compute this Q again, you maximize it again. Now you have your next guess, and so on and so on. I'll show you some visuals of what's happening here, but that's kind of at a high level. And when we do this estimation step, we think of these Z variables as these hidden variables. We think of them as like there is some true value of them, and we're trying to figure out what is the true value. And so we want to try to estimate what is the true Z, the true hidden variable. And so if you kind of drill down into this expectation, so what is going on here? So this conditional expectation, we have an integral over Z, because Z is the random variable, X is fixed. And so we know that, okay, if you have this conditional expectation, this thing appears here, and then the probability that we're using for the expectation appears here. And this probability is a probability over Z, given our fixed data X and given our previous guess of theta T. And so that's kind of what this is. And the intuition behind this expression here, is that you're not really sure what the hidden variables are. You kind of you think, well, I think my hidden variables are these, but you have some uncertainty about them. So that's where this notion of this PMF is. So this PMF might have like a peak to it, and that would be your best guess of your hidden variables at that iteration. But then it has, some decay to it, and that tells you that, well, it could be these other things. I don't know. But if you take an extreme case where you were absolutely sure that your hidden variable was, we'll call z hat t, that would be the case where this PMF is this delta function. The delta function is like the Dirac delta, where it's like a probability distribution with all the mass centered at one location. And if you've taken, I don't know, I think it's taught in a bunch of signal processing classes, if you put one of these delta functions in this integral, then essentially what happens is you get out this with this sampled. So if you're absolutely positive that z is exactly this number, then this q function here is just going to be that joint probability evaluated at this value of z. Okay. But more generally, you're not sure, you're not this sure. So what this does is it is sort of like an average of this over all your hypothesized, your belief about z. Okay, so it's kind of what this thing is doing for us. Okay, so I'll next try to explain like what is going on here. Why do things have this form? And we'll do it step by step. Okay, so let's say that we have, here's our log likelihood. This is the thing we want to maximize over theta. And this is our fixed data x. So let's say that someone gives us a belief on a random variable z. And we'll just call this p hat to distinguish it from this p. So we know that if this is a valid PDF, then we know that if you integrate this over z, it is exactly 1. So you can imagine this outside, and then what remains here is just equal to 1. So this equals itself times 1. That's the first step. And then the second step is move this thing inside that integral. Notice that this can be moved in or out of the integral because it doesn't involve z. Okay, so does everybody understand where this equality comes from? Okay. So next we're going to play another kind of game that is not intuitive. We're going to rewrite this in a very complicated way, which is this. Okay, so let's see how this goes. So you can see that these cancel. And then what remains is a very complicated way of writing this. So, and where does that come from? So, okay, so probability of z and x, I'll omit the thetas. As we know, we can write that as probability z given x times px. And then in the denominator, we have probability z given x. So that's this ratio. And now on the right, we have this. So you can see that this is px. Okay. So this is just kind of to show you that you can take px and you can write it in this crazy way, which is what we've done over here. Okay, now there's a reason we're doing all this. So does everybody agree with this last equality? Okay, so now remember that if you have like log of a over b, that is equal to log of a minus log of b, and log of a times b is log of a plus log of b, and so on. So that allows us to rewrite this log as a sum. We can write that big log as log of this minus log of this plus log of this. So here's log of this part, and then minus log of this part, and then log of that. And we can, so then we have the sum of things inside the integral, and we can split that into 3 different integrals. Okay, so these integrals each have a meaning. this one is basically the log of this joint distribution, sort of averaged over all the different, over your belief on Z. So as I said before, you're not really sure what Z is. You think it might be this or that. And so this is kind of like just your average value of this over your belief. So we'll write that as expectation, and we'll put this little p hat down here to remind us this is an expectation under this belief. Okay, this next term from information theory is known as the entropy, and it's the entropy of this PDF. So basically it just tells us it's some measure of how much randomness is in that PDF. And then finally, we have a term also from information theory called the Kullback-Leibler divergence, which is probably the most common way of comparing two PDFs. If you want to know how different two PDFs are, this is usually how you do it. So the two PDFs in this case are p hat is one PDF and this is the other PDF. And this divergence has a property that when this and this are equal, the divergence is 0. I think you can see that immediately because if those are equal, their ratio is 1, and then log of 1 is 0, right? And you have 0 inside the integral, you get 0. So, and the more different that those two PDFs get, the larger the divergence is. So this is a quantity that is non-negative and gets bigger as the two PDFs get more different. Okay, so we've broken our likelihood into these three terms. And because this guy is non-negative, if you take this away, this is either equal to this or less, right? Because if I take something positive away, what remains is smaller than this. So basically, this is a lower bound on our likelihood, our log likelihood. So this is written here. So our log likelihood is lower bounded by the first two terms, these two terms, because this guy is non-negative. And this is a quantity that is given a special symbol for us. We'll define the symbol as this script L. This is a lower bound on our log likelihood. And this is why it's useful. Let's say that this picture on the right shows me my log likelihood. So the log likelihood is this triangular shape. And then this is, let's say, theta is, in this case, just a scalar parameter. Now, our favorite way of maximizing log likelihood has been to set the derivative equal to 0, right? Or use gradient descent, in which case you repeatedly evaluate the derivative, and you use that to guide you. Well, there's a problem here. This is not differentiable at this point. Let's just assume that this continues down. Sorry. So what happens if you apply gradient descent to this? Let me ask Elena Sun? No. What about William Huang? Almost finished my attendance here. Okay, what about Yingzhe Zhang? No. Okay. Great. Okay, so anybody have an idea of what happens if you apply gradient descent? So remember, our goal in this case is we want to find the theta that maximizes this. We want to find this theta, right? Well, we want to do with the gradient descent. What's going to happen?
Does not exist at the maximum.
Yeah, but I'm saying, let's say I start here. The derivative exists there, right? So I can apply gradient descent. What's going to happen if I apply gradient descent?
You go up.
I go to the right. And how far right do I move? It's according to my step size, right? So let's say that I move over here. Now what happens? Next step. Go left, right? But these have the same slopes. So I go back. And so I just bounce back and forth, right? If you decreased your step size with gradient descent, you could eventually get to the peak. Never exactly to the peak, but you'd get closer. But fixed step size gradient descent would just alternate, bounce back and forth, do nothing. If this was quadratic, you wouldn't have that problem because as you get closer to the center, the slope gets smaller, right? So you take smaller steps. So it's kind of like self-adjusting. So this is just an example of the issues you have with non-differentiable cost functions that they show up, things like this. So that's why we don't want to just use gradient descent to solve this problem. So here's another idea, which is kind of a cool idea, and it's basically the idea that EM is using. So let's say you come up with a lower bound on this log likelihood. And let's make a nice tractable lower bound, which is this kind of quadratic shape. So here, this is a lower bound, right? You can see that this is always less than our log likelihood for all theta. And we want to make this a tight lower bound, meaning there's some theta at which point it equals this. So this is tight. If it was over here, it wouldn't be tight. But this is tight because right there, it's tight at that point. So the idea here is you alternate between tightening your bound and optimizing using your bound. So you might say, well, this thing is too difficult for me to optimize directly, but this one I can optimize in closed form because it has this quadratic shape. I know that its peak is right here. So we start with this lower bound. We optimize it here, and we say, okay, make a new lower bound that's tight there. So now you would have another quadratic that would be tight there, and it would kind of come down like this, maybe. And then you would repeat. Now you say, okay, now this lower bound is very tractable, so I can optimize this, and I will make a new lower bound that's tight there. Okay. Do you see how this process works? So it's this iterative where you make a lower bound that's easy to work with, maximize it, then tighten it, maximize it, tighten it, maximize it. So that's the whole name of the game. Tighten your lower bound. In this case, it's this log likelihood lower bound, and then maximize it through choice of theta. So, okay, is that idea kind of clear?
Couldn't this also overshoot if you don't make it tight enough? Like if you make your quadratic too wide, and let's say you're like almost at the peak.
In this case, it would converge to the peak. Yeah, you'd get closer and closer, and eventually it would be like there, and then you'd optimize it. It would be right there. I mean, it wouldn't happen in a finite number of steps, but like.
Oh, it just keep getting tighter and tighter.
It would keep getting closer and closer to the middle, and
Gotcha.
And it would. Your steps would get like smaller and smaller, just like you would want in gradient descent to happen. Yeah. Okay, so that's kind of the high level idea, and it's a powerful idea that you can use for any kind of like iterative maximization problem where it's too hard to solve directly. You come up with a lower bound, and then you optimize your lower bound, and then you tighten it, optimize, tighten, optimize, tighten. So that's what we're doing here. Now, when we look at our lower bound, this guy, it's really a function of two variables. One are the variables we're trying to optimize, these thetas. And there's another thing that determines, the tightness of the lower bound. And it's actually all about this term, right? Because we know when the KL divergence is 0, that it's as tight as can be. Because if this is 0, then this equals our log likelihood. So the clear way to tighten our lower bound is just to set the KL divergence to 0. And the way to do that is to set your belief equal to this at your old theta. And that is exactly what's happening here. So, So this is the quantity that we have in our EM algorithm. This is exactly the quantity here. The belief, p hat, is exactly this, where we have used the previous value of theta. So hopefully now you can understand what is happening here. This is tightening your lower bound over theta. And then, this is the tightening step, and this is the maximizing step. Okay, so I apologize, I've gone over time, but we can continue the discussion later. This is the idea. What I've actually described for you is a little bit more general than EM. It is called majorization minimization. That's the general idea. And EM is just like a special case of this when it is applied to this log likelihood. But this majorization minimization is sort of like a generic optimization approach of making a lower bound and tightening it, lower bound and tightening it, and so on. Okay, have a great weekend. See you guys on Monday.